This question is about different pH values. For pure water at 40 degrees C, pH equals 6.67. A student thought the water was acidic, possibly because pH was less than 7. Explain why the student is incorrect. Well, the reason that pure water is never acidic is because in pure water, the hydrogen ion concentration is always equal to the hydroxide ion concentration, and therefore there is not a greater concentration of hydrogen ions, which is what makes something acidic. Then it says find the value of Kw. So the first thing we're going to do is use the pH to find the concentration of H+. So 10 to the minus pH. So shift, press the log button, minus 6.67. So I'm getting 2.14 times 10 to the minus 7 moles per decimetre cubed H+, which means that the OH minus is the same as that. So remembering that Kw is H plus concentration times OH minus concentration, and these two numbers are identical. So I'm just going to take the answer on my calculator screen and square it. And I'm getting 4.57 times 10 to the minus 14. Now the next part of the question says sodium hydroxide solution was added gradually from a burette. So we've got in a beaker here 25 centimetres cubed of 0.08 mole per decimetre cubed of our weak acid propanoic acid HA, and we're adding sodium hydroxide from a burette, and we're getting values shown in this graph here. They're measuring the pH. Use the value, figure 4 to determine the value of Ka. Okay, so this is using some knowledge from the required practical that the Ka value can be found from the pH at half equivalence. So the first thing I'm going to do is find out where equivalence is. So I'm going to go to the centre of the straight line, and I'm going to read off. Just undo that because the iPad pencil is just a tiny bit thick, so I'm just going to move my ruler ever so slightly so that I can then go from the centre of the straight part down to the bottom. Read that off and see that that is 19.6 centimetres cubed. So then I'm going to go to half that on my calculator. So that's 9.8. So then I'm going to go along to 9.8 and I'm going to draw a vertical line up to the curve from 9.8. And then I'm going to read across. So just slightly overshot the graph there, so I'll just come back down a tiny bit. Now it looks like it's coming out at 4.9. So the pH at half equivalence, so it was equivalent at 19.6, half of that is 9.8, the pH is 4.9. So pH at half equivalence equals 4.9. And the pH at half equivalence equals the pKa. So that means that the pKa equals 4.9, which means that the Ka equals 10 to the minus 4.9. So I'm going to do that on my calculator and get 1.26 times 10 to the minus 5. Suggest which indicator is the most appropriate for the reaction in 9.2. So if we go back, we need an indicator that lines up with this vertical portion of the curve. So sort of from around 6.5 to somewhere just above 11 at 11.2, something which has a range that falls fully within that area. So which one's the most appropriate? So 11.2 was our end. We don't want to be higher than that. 6.5, we want to be higher than 6.5. So that's not higher than 6.5, that's not higher than 6.5. Cresol looks like our most appropriate. Next part of the question says a student prepared a buffer by adding 0.0136 moles of the salt to, we've got a volume and a concentration of the acid, HX. Then they added some OH minus, which is a strong base. So in our buffer, we've got a mixture of weak acid and salt. Which one would OH minus use up? It would use up the HX. So HX would react with the OH minus to make more X minus and some water. How much HX did we have at the beginning? Well, we had 100 centimetres cubed of 0.5. So we need to work out how much that is in moles, 0.05. We had 0.0136 of this. This is at the beginning, before anything reacted. And we put in 3 times 10 to the minus 4 moles of this. So after those have reacted, what have we got left? Well, the sodium hydroxide disappears, it goes down to 0. So this one will also react in the same proportions. And so we'll have 0.0497 moles of HX after we add the alkali. And we'll have made some more salt. So we're going to add 3 times 10 to the minus 4 to our 0.036. And we get 0.0139. So these are our moles after addition. Now, if we think about the Ka expression, because we've been given the Ka, it goes H plus times X minus over HX. And to find a pH, we need to find H plus. So H plus equals Ka HX over X minus. And because it's a buffer, you can't use any squared or square rooting because nobody is the same as anybody else. Now there is a little trick now, because if you notice, these are concentration brackets. So our Ka value, I'm just going to put the Ka value in, 1.41 times 10 to the minus 5. We're going to times by HX, which is 0.0497, divided by the volume, whatever the volume is. And then we're going to do X minus 139 divided by the volume. Actually, we don't need to put the volume in because we can see that the volume is going to cancel because there's equal on the top and the bottom. So we're going to type that in our calculator and we're going to get 5.04 times 10 to the minus 5. And then we're going to do pH is minus log of hydrogen ion concentration. So we're going to do minus log of our answer on our calculator. If we type that in, we're going to get 4, and remember 2 decimal places, 4.30. A buffer solution has a constant pH even when diluted. Use a mathematical expression to explain this. So remember that the pH of a buffer is calculated by finding the H plus that you've just done by doing Ka times HX over X minus. Now what happens when you dilute it is you change the concentrations of HX and X minus, but you change them the same amount. So HX and X minus is constant upon dilution. So pH is constant. It's quite difficult phrasing of the question actually, because it's not exactly a mathematical expression. The idea is that the HX and the X minus are going to change in the exact same proportions and therefore they're going to stay constant. So pH is going to stay constant.